In this video, I'll explain what is Cauchy integral theorem and hence Cauchy integral formula. See, the Cauchy integral theorem states that if f of z is analytic in simply connected domain D, then for every simple closed curve C in D, the line integral of f of z with respect to z over the curve C is always equal to 0. This is the statement of Cauchy integral theorem. If the condition is f of z is analytic, then over any simple closed curve C, its value of the integral is always equal to 0. Let us take one example. Evaluate this integral over C, where C is given by a circle. Mod z equal to 2 means it is a circle with the radius 2 units. So when you plot this circle, we will get radius is 2 units. Therefore we will have, this is the representative diagram of the circle. This is the circle, radius is 2 units. Therefore now the given function f of z, we have to check is it analytic within this closed curve C. So C is a circle with center at the origin and radius is 2 units, and the function f of z equal to z square by z minus 5. This function is not analytic at z equal to 5. F is not analytic at z equal to 5, because this becomes 0, denominator becomes 0, the function is not defined, therefore it is not analytic at z equal to 5. Though it is not analytic at z equal to 5, that z equal to 5 won't come within this closed curve, because radius is 2 units, hence 5 comes, which is away from this value 2, which doesn't come within this closed curve. Therefore this function is analytic at every point within this closed curve C. Thus, by Cauchy integral theorem, integral of z square by z minus 5 over the curve C is always equal to 0. Cauchy integral formula. Cauchy integral formula is given by, see, the conditions are, let f of z be analytic in a simply connected domain D, then for any point z0 in D and any simple closed path C in D that encloses this point z0, we have this formula. The line integral over the curve C, f of z by z minus z0 with respect to z equal to 2 pi I into f of z0. So this formula you have to remember. This is called as Cauchy integral formula. So from this formula we can write f of z0 equal to 1 by 2 pi I integral over C f of z by z minus z0 into dz. The conditions to apply this integral formula is that the function f of z, whatever you choose, should be analytic in the simply connected domain D. Let us see few examples to understand how to apply the Cauchy integral formula. Now consider one example. Evaluate this integral over C tan z by z square minus 1 with respect to z, and the closed curve is a circle with center at the origin and radius is 3 by 2 units. So first let me write the Cauchy integral formula. Integral of f of z by z minus z0 over any closed curve C is given by 2 pi I into f of z0. So first, this is the given function. This is not f of z. We have to find out f of z such that the function f of z should be analytic. That is the condition for Cauchy integral formula. So this is the given function. So in this given function, first you have to find out singularities of this function. Singularities means the points at which the function is not analytic. The points are z equal to 1, z equal to minus 1, because 1 minus 1 it becomes 0, denominator becomes 0, function is not defined. Even if you put z equal to minus 1, again 0, function is not defined. And other singularities are plus or minus pi by 2, plus or minus 3 pi by 2, odd multiples of pi by 2. That is because tan is not defined for odd multiples of pi by 2. Now, out of all these singular points, these points pi by 2, odd multiples of pi by 2, doesn't lie within this closed curve, because the function should be analytic within the given closed curve. Anyway, these points won't be included within this closed curve, because radius is just 3 by 2, 1.5 units. Hence you can exclude these points. Now z equal to 1 and minus 1 are inside this closed curve, that is circle, mod z equal to 3 by 2, because 1 comes here, the radius is 1.5 units, 1 is within this closed curve. Similarly, minus 1 is also within this closed curve. Therefore, we are splitting the given function in terms of these singular points 1 and minus 1. We are avoiding these points, these are odd multiples of pi by 2, because they are not within the given closed curve, because the function, given function, should be analytic within the given closed curve. Now, therefore, I will write this integral now, tan z divided by z square minus 1 into dz equal to, this is equal to z square minus 1 can be written as z plus 1 into z minus 1, z plus 1 into z minus 1 into dz. This is equal to tan z into, to simplify it further, I will write z plus 1, 1 by z plus 1 into z minus 1, as using the concept of partial fractions. This can also be written as 1 by z plus 1 minus 1 by z minus 1. Now this gives you z minus 1 minus z minus 1 minus z plus z cancels, minus 1 minus 2. Minus 2 is extra, so I will divide it by minus 2 also. This is over the curve C. This is equal to, now, minus 1 by 2, let me keep it outside, over the curve C, tan z divided by z plus 1, then minus integral over the curve C, tan z divided by z minus 1 with respect to z. Here also with respect to z. Now you can apply the Cauchy integral formula. That is because compare these two functions with this formula. Now f of z is tan z, which is analytic within this region, because tan z is non-analytic for all these points, but those points are not within this given circle. Hence, this tan z is analytic at every point within the given closed curve. Therefore, this function f of z is analytic. So here f of z equal to, I will write if you want, f of z equal to tan z in both the cases. In the first case, z not equal to, this z not equal to minus 1, and here z not equal to 1, and f of z equal to tan z. Therefore, let us apply the formula. This is equal to 2 pi I into f of z naught is minus 1 minus, here you have minus 1 by 2 as it is. This is 2 pi I into f of, this is 1, because z naught is 1 as per the given Cauchy integral formula. So this is equal to, let me simplify it further. This gives you minus 1 by 2, and 2 can be 2 pi I can be taken outside. Then f of minus 1 is tan of minus 1 is minus tan 1. Tan 1 is nothing but for 45 degree, that is minus pi by 4, minus f of 1 is again pi by 4, because tan of pi by 4 is 1. So this gives you 2 cancels, minus pi I into minus 2 pi by 4, which gives you minus pi by 2. Hence the final answer will be minus of minus plus pi square I by 2. Now next is generalized Cauchy integral formula, or generalized Cauchy integral theorem. This is to find the derivative of analytic function, any nth derivative of analytic function. This can also be used to evaluate some of the integrals. Let us see what generalized Cauchy integral theorem says. If f of z is analytic in the domain D, then its derivative at any point z equal to z naught is given by if nth derivative of z naught is equal to n factorial by 2 pi I integral over the closed curve C f of z by z minus z naught to the power n plus 1 into dz, where C is simple closed curve in D enclosing the point z naught. So let us illustrate this using one example. Evaluate. I want to evaluate this line integral where the closed curve is a circle with the radius 3 units. So this circle is having the radius 3 units. So directly you can't apply because you have to get f of z as an analytic function. This is the given function. Now I have to get analytic function out of this. So first you have to, whenever any function is given, first you have to find out the singularities of this function. So singularities of e to the power 2z by z plus 1 to the power 4 are, there is only one singular point. Therefore, you have z equal to minus 1 as the singular point of this function. Singularity means the function ceases to be analytic. As z equal to minus 1 is within this closed curve, closed circle, because here comes minus 1, minus 2, minus 3. Therefore, the function, entire function can't be chosen as f of z because the function should be analytic in the given closed curve at every point z equal to z naught. But at this point, it is not analytic. Therefore, this entire function can't be chosen as the f of z. But e to the power 2z is analytic at every point of this closed curve mod z equal to 3. Therefore, what I'll do is this function f of z, I'll choose it as e to the power 2z. This function is chosen as f of z now. So, as per the Cauchy integral theorem, generalized Cauchy integral theorem, f nth derivative at z naught equal to n factorial by 2 pi I integral over the closed curve C f of z by z minus z naught to the power n plus 1 into dz. I have chosen generalized Cauchy integral theorem because you can always look at the value in the denominator. If it is having power more than 1, then usually it goes with the generalized Cauchy integral formula. Otherwise, the usual Cauchy integral formula. Now here compare this with the given value n equal to, here this power is equal to 4. Therefore n must be equal to 3 because 3 plus 1 equal to 4, and z naught is equal to minus 1 because this is the point at which there exists a singularity for the given function. So always that z naught is chosen where the singularity of given function exists. So z naught equal to minus 1. Therefore, we want fn means 3, third derivative of f of z. So, f dash of z is 2 into e to the power 2z, f double dash of z equal to 4 into e power 2z, and f triple dash of z equal to f triple dash of z equal to 8 into e power 2z. This is the third derivative. So, we want the third derivative at the point z naught. So, f triple dash of at the point minus 1 is equal to 8 into e power 2 into minus 1. So that is 8 into e power minus 2. So this value let me substitute here. 8 into e power minus 2 is equal to n is 3 factorial divided by 2 pi I into integral over the closed curve C. F of z is e to the power 2z divided by z minus z naught is minus 1. So minus of minus plus 1. 3 plus 1 is 4 into dz. Now look at this. This is what the given function. We arrived at the given function. Now simplify to get the value of this integral. So keep this integral here itself as it is. Now this 8 by e square into, this comes to the left hand side, 2 pi I divided by, here 3 factorial is 6 is equal to this given integral z plus 1 to the power 4 into dz. So now when you simplify all these, we will get the value of this integral as this is equal to, I will write here, this full integral is equal to 8 pi I divided by 3e square. You can check with this, 2 ones are 2 threes are 8 pi I divided by 3e square. This is the value of the given integral which is evaluated using generalized Cauchy integral theorem.